Okay, so in this video, I am going to teach you how to calculate the molar mass or the atomic weight of a compound. Now, this is a very vital step to learn just because in chemistry you can't really move forward without knowing how to do this step, how to calculate the molar mass or the atomic weight of a substance. You can't really move on to stoichiometry and do complex calculations without knowing how to do this. So in this video, we are going to go over some examples, and I'm going to teach you my method for calculating molar mass and the atomic weight. So the first things first, molar mass and atomic weight are kind of synonymous in my vocabulary. If your teacher talks about it in molar mass terms, then molar mass it is. If your teacher speaks about it in atomic weight terms, then atomic weight it is. They're kind of the same thing in my book, so just to not confuse you. Now, to calculate the atomic weight or the molar mass of a compound, all you need to do is simply add up the atomic weight of each of its atoms in that compound. So you might be asking yourself, so where is the atomic weight of each of the atoms? Well, it's in your periodic table. So when you look at your periodic table of elements, so here is my copy. So if you look in the bottom of each of the little boxes, so for hydrogen, its atomic weight is 1.008. It's that little bottom number. It's hard to see on this periodic table, but if you zoom in, you can kind of see sodium's is 22.990, etc., etc. So each atom on the periodic table has an atomic weight associated with it. Now, scientists, when they discovered what each atom's atomic weight is, what they did is they did a weighted average of every variation of this atom in existence. So for example, sodium, atomic number 11, it might have 12 isotopes in the wild. It might have only 9 neutrons in its nucleus. It might have 12 electrons, out in the wild. So there's so many different variations of sodium out there, but it's still sodium. And so what scientists did is they took the weight of all the different variations of sodium they could find, and they just grouped it together and did an average of all of them. And that is the number that you see in the official periodic table, the average that you see. So, another thing that is worth mentioning is atomic weight. Its units is in atomic mass units. Sometimes you kind of see them in grams per mole too. So it depends on what you see out there. Sometimes you see them in atomic mass units or AMUs, and sometimes you see them in grams per mole. It's just kind of what your teacher, prefers. Now, atomic mass units are very, 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 very small weights. I actually looked up what one atomic mass unit weighs in pounds. So one atomic mass unit is equal to 3.6 times 10 to the negative 27th pounds. So it's a very, 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 very small amount of matter, and it's a very, very small amount of weight that we're talking about here. We're not talking, a huge weight. We're talking about very, very microscopic molecules here. So moving on. So finally, we're going to get into some examples of how to calculate atomic weight or how to calculate molar mass. So like I said, you just add up the atomic weight of each of the atoms that are found in that compound. So the first one here, we have sodium chloride, or NaCl. So the first atom we have here is sodium, that Na. We go up to our periodic table, and we find Na's atomic weight. It's 22.990. 22.990. All right, we go on to the next atom in our compound. Our next atom is chlorine, and chlorine has an atomic weight of 35.453. So when you add those up, you get a total of 58.443 AMUs, or sometimes, if your teacher likes it this way, grams per mole. And all we did was we added the atomic weight of each of those atoms. All right, the next one. So we have potassium hydroxide, or KOH. So potassium, so we go up here, we found potassium, it's 39.098. Oxygen is 15.999. Finally, hydrogen, 1.0078. So we add those up. We get a total of 56.1048 AMUs, or sometimes we see it reported as grams per mole. All right, the next one. So this next one's a little bit trickier. So let's find our molar masses for the first atom, which is magnesium. So let's go up here, let's find magnesium. Magnesium is 24.305. So 24.305. Chlorines, which we already have from the previous problem, was 35.453. All right, but if you're looking at this compound, we actually have two chlorines. So we're going to have to multiply this chlorine by 2 since we have 2 atoms of chlorine in our compound. So when we add those up, we get 95.211 AMUs, or grams per mole. Finally, we have magnesium hydroxide. So the first atom we have is magnesium, which we found its atomic weight in the periodic table to be 24.305. Oxygen is 15.999. Hydrogen is 1.0078. But if you're looking at this, we have 2 hydroxide units. We don't just have one OH, we actually have 2. And that's why we have parentheses 2. It's meaning we don't just have 2 hydrogens, we also have 2 OHs. So if you look at this, it's like saying this. MgOH. That's kind of what it's representing. Now, you wouldn't write it that way, but that is what that notation is representing. It's representing that we have two hydroxide ions. So, since we have two oxygens, and we have two hydrogens, we're going to multiply the oxygen's weight by 2 and the hydrogen's weight by 2. And when you add all of that up, a lot of calculating, a lot of calculators, you'll get 41.3118 AMUs or grams per mole. So again, just as a review, we're simply adding up all of the atoms' atomic weight from the periodic table to get the total molar mass of the compound. I hope this cleared up questions or any confusion that you have on this topic. If you have any questions, please leave them down below, and have a great day. Thank you all.